Alright, so this problem is practice with sort of the directions of forces as a car moves through circular inclined plane and then linear motion. And so it's practice with kind of components and recognizing directions of forces. So part A kind of gets us started by doing a general free body diagram for the car when it sits at rest. So our ball hangs straight down, and there's a tension that pulls up, and there's a weight that pulls down, and that's it, right? Because it's at rest, they're in equilibrium, so we can write the net force equals 0, or the tension minus mg, the weight, equals 0, or the tension equals mg, and if you plug in the numbers we're given, right, 1 Newton, right? I'm going to use G as 10 for this, just for fast calculations. If you use 9.8, you get slightly different numbers, but it doesn't really change. Okay, so there's part A. In the other parts, we're not going to change the forces, we're just going to change their magnitudes and directions based on the motion that's described. So, part B, we have our car kind of like this, and it's attached right here, and there's it's kind of sloppy, and there's the vertical line. Actually, let's see if I can do this actually better. Okay, there's our roughly vertical line. Okay, and so we're told the car is moving to the right with an acceleration, right? So there's an acceleration like that. So in terms of drawing, right, you can draw and calculate in either order. I think that in a lot of cases the drawing's easier. So for it to accelerate to the right, we need a horizontal force, which means the string must partially pull to the right because the weight will always be straight down. So it means it must look like that, something like that. And so we can figure out the components by saying the sum of the vertical forces equals 0, right? It's not accelerating up or down. So this is tension times well, actually, we don't need the components, right? The vertical tension minus the weight equals 0, or the vertical tension is 1 Newton, right? Because we already calculated that. And then the horizontal part is what causes it to accelerate. So this is TH equals MA, right? And 0.1 times 5, 0.5 newtons, right? So you see by our combination of sort of the vertical part is in equilibrium and the horizontal part is accelerating, we can calculate both components of the forces. So from that way I could put it together and tell you the total tension, right, using the Pythagorean theorem, but we're not being asked for that, so that's okay. Okay, point C. We draw our car again, and vertical. Actually, that's probably a bad drawing because I need it to be tilted. Right, in part C, we're on an incline. Right. So it's going to look more like this. Right. Okay, there. So there's our vertical. There's our attachment point. So we're going up an incline, but we're going up at a constant speed. So that means we can't have a horizontal acceleration, and we can't have a vertical acceleration, right? It stays in equilibrium. So that means the ball hangs straight down, and so the vertical forces, net force is 0. So once again, the vertical tension is 1 Newton. It's not accelerating horizontally, so the net force in the horizontal direction is 0. And that tells us immediately that the horizontal tension is also 0 newtons. Now you notice in this problem, I'm not using the tilted coordinate system that you normally would for an incline, and that's because I want to be able to compare, like, between these statements. So I need to use the same coordinate system for both. All right. If I only asked part C by itself, then you could do it as a tilted coordinate system and talk about the amount of tension that points up the incline and the amount of tension that points into the incline and talk about those components. But because we want sort of consistency in comparing parts, we're just going to keep the coordinate system in just sort of a regular x and y. Okay, so that's B and C. You have something similar for D and E, but D and E are a little bit trickier. So D, we're going down an incline. But we're accelerating down the incline. And so this is where that coordinate system part is a little bit tricky. Actually, do it like this. If our total acceleration is down the incline, we can break the acceleration up into components as well, right? And now we can, instead of doing our tilted coordinate system with one acceleration, we can talk about the acceleration in two directions and talk about the x and y forces. Right? So in the x direction, actually I guess I should draw it in first. You should probably know what's going to happen, right? The ball is going to kind of hang out backwards, kind of like that. So in the x direction, the only possible force remains tension. So it must cause the horizontal acceleration that we see, which is m a, and if we look at the components, we see this has to be cosine of theta, where that's the 30 degrees. This is theta. So m a cos theta is 0.43 newtons. So the vertical part is done pretty similarly. Oh, oops. And I realize here I forgot a sign, right? This acceleration is in the negative direction. So we have a negative in there. And so if you have negative ma sine theta plus mg, you end up getting 0.75 newtons. Right? So the trick to this one is splitting up the acceleration rather than splitting up the forces. Part E is the part where we're actually sort of dealing with the circular piece. We are upside down, right? So there's a vertical line. And so the question is, what's the string doing here? Well, we know there's no tangential acceleration, which means our only equation to write, right, horizontal would be tangential in this case. So this is, right, that's kind of the result we've been getting for a while, no horizontal tension. The vertical is going to be solved like this. And in this case, both mg and mv squared over are point towards the center of the circle. So this is correct signs. And so this is going to be 1.5 newtons. But you notice that from directions, 1.5 newtons pulls down, which means the ball must be up here and the string pulls down, so it's straight up. Right? So the string has not gone slack or anything like that. And so those are the various parts where we talk about the components of the forces that cause the ball to kind of move around inside the car as the car moves.